This conference will now be recorded.
Good evening, madam. I have started already, so I will continue. So, good evening, students. Today we are starting a new chapter. Here also, so this chapter is web optics today. Here also, we'll continue discussing various questions from previous year's papers, JEE papers. So, in the web optics, excuse me. So, interference, diffraction, and polarization, these three parts are there, subtopics are there. So today I have actually taken up maximum questions from interference. Okay, so let us start today's discussion. So in a double slit experiment, instead of taking slits of equal width, so this is actually talking about Young's double slit experiment. You know that. So you have two slits of equal width in general. Okay, you have a screen over here, and light goes and interfere and in this screen, and see when you see the central maxima will be like this, and then you will have alternate maxima and minima over here. Okay, bright and dark fringes over here. So that is what we know. So this distance, generally the distance between the slits is written as d, sometimes d by 2 or 2d, etc. And here it is capital D, the distance between the screen and the slits. So this is D. Okay, now in this question it is said that in a double slit experiment, instead of taking slits of equal width, generally this width of this are taken as the same. one slit is made twice as that of the other slit. Then in the intensity pattern, how the intensity pattern in this interference will change. Okay, so how will this change? I'm sorry, how will this change? Interference pattern will change. Generally we know central maxima. If I just draw here, so it used to be like this, and then consequently, oh sorry, I'm sorry, here in case of interference, the intensity of all the fringes will be the same actually. Okay, but there will be dark and bright fringes. Here the intensity will be maximum, then like this intensity maximum, in the sense this will be actually bright fringe, central bright, then you will have other bright fringes and dark fringes like this. Okay, on either sides. Okay, so what we have to see here, the intensity of both the maxima and minima increases, whether intensity of the maxima increases and minima has zero intensity, the intensity of the maxima decreases and that of the minima increases. Intensity of the maxima decreases and minima has zero intensity. I'll just repeat the question once again. See, in case of normal YSD E, so Young's double slit experiment, generally width of these slits is to be same. Okay, so central maxima, in the sense there will be central bright fringe, and then maxima and minima will come. Okay, so these are say minima and these are maxima. Okay, if I draw this is the central maxima, then there will be minima like this. Intensity will be the same actually. Okay, on either sides there will be like this. You might have now you might be able to remember. Okay, generally central maxima, if we just see the width, central bright maxima actually. This is central bright maxima in the sense its intensity will be maximum. This is central bright maxima and others are here. Okay, this is central C, this is dark. Okay, this is bright, this region is dark, this is bright again. So dark bright, it will go like that. Okay, so the question is when the width these were same. Okay, suppose width were some d. Okay, both the cases. Okay, now the slit widths are changed. Suppose one is twice the other. So this is suppose d and this is 2d. So what will happen to the intensity? How the intensity of the pattern will change? Whether the maxima intensities of both the maxima and minima increases, then intensity maxima increases, minima remains 0. In general, minima should be 0 when the widths are equal. But what is the case here? Whether it will be 0 now also when the slit widths are not equal, then intensity of the maxima decreases and minima increases. And last option is intensity of maxima decreases and minima has 0 intensity. Now we'll try to understand how intensity depends on the width. See, intensity depends on the width directly, okay? Or you can say, yes, it depends on directly, okay? It depends directly. So I'm saying this D. So intensity directly depends on the width, slit width. So I can say that now I have two sources, S1 and S2. This is slit 1 is sending intensity I naught, and the other one is sending intensity of light I 2 I naught. I hope it is clear to you. So intensity is directly proportional to the width of the slit. Now then in my experiment, now I have two sources, coherent sources. One is sending light of intensity I0, another one is sending a light of intensity 2I0. This is the difference. Now what happens in case of the central maxima? In central maxima, you know, intensity adds up. In central, sorry, not central, I'm sorry, the maxima, intensity of maxima, how it will be, intensity of the light, incoming light will be added up. Okay, added up. So it will be I0 plus 2 I0. Okay, let us say 2 I0 plus I0. Okay, so this will be actually added up. So earlier how it was? Earlier, suppose it was I0 with D, 2 now it becomes I0, I0, 2 I0 it was earlier. Now it is, because earlier intensity was same for both. So earlier it was 2 I0. Now intensity will be increased. Okay, let me just give you the uh, general intensity, general equation for intensity of the interference pattern when you know the intensity of both the lights coming up. So this is I2 and cos phi. So where this phi is the phase difference. So this is the general expression for intensity pattern, intensity pattern, sorry, intensity of the pattern, interference pattern. So if the cos phi, if phi is 2 pi, then it will be it will be constructive interference, right? Okay, so if it is 0, so phi is 0, I'm sorry, phi is pi by 2, then it will be 0, and this will be I1 plus I2. Okay, so constructive interference if phi is 0, in the sense you can just think of in this way also, this will be root I1 plus root I2 whole square. Okay, this will be the maximum intensity pattern. And minimum, what will be the difference when it is -1, when this cos phi part is -1. So it will be this one. Okay, even if you, okay, just ignore it now for the time being. So this is general formula for the intensity of maxima and minima. So you can see intensity in this case also increases, because earlier these two were equal, so minimum intensity was 0 earlier. Okay, now these are not same, so that's why the intensity, so intensity will be, see if I just put it here now with this, Imax is going to be see 2, so this is plus 1, right? Here I can just directly write I1, that means I0 plus 2I0 plus 2 into I0, 2I0, so root 2 I0. Okay, so at least you can see this is 3I0 plus this term. Earlier you would have got I0 plus I0, 2I0, okay, or 4I0 you would have got. Now you have got this term also with this. So you have now this. Earlier what you would have got I0, I0, so this will be again 2I0, and this is, so you would have got 5I0. Now it is actually, see this is more than 5, because this root 2 will be 1.4 and you have 2, so 2.8, so 5.8, something like that. Okay, 5.8 nearly. Okay, it is increased. Okay, so it is increased. Now minima also, you look here, if we just put it here with the minus sign, say I0 plus 2I0 minus 2 root 2 I0. So this is 3I0 as we know, and this is 2.8. At least now it is nearly 0.2 I0, which is not equal to 0. See, it will not be 0. See this minimum intensity in general we know it is 0 for interference pattern, but in this case it will not be 0. So both the maxima, intensity of maxima and minima increases. I hope I could explain you, or you are satisfied with this. So what is the point here? The point is that you have to know the expressions for the maxima and minimum intensity, okay. Then you can just think here that slit width is directly proportional to the intensity of the light coming from both the slits, okay. If the if the slit width increases with the same with the same proportion, the intensity of the light also will increase. Okay, we'll go to the next. So here two beams of light having intensities. See here, intensities I1 is given as I and I2 is given as 4I. Interfere to produce a fringe pattern on screen. If the phase difference between the beam pi by 2 at a point A and pi at point B, then the phase difference between then the difference between the resultant intensities at A and B will be how much? Difference you have to find out, resultant difference. Okay, so we'll solve this question. So we know the general formula for intensity I had just written for you. The general formula is I1 plus I2 under root 2 under root I1 I2 I1 I2 cos of phi. So phi is the phase difference. So here look at I intensity at A point where phase difference is pi by 2. So pi by 2 means this term will be 0. So I get I1 plus I2. Okay. So I1 plus I2 means how much? It will be I plus 4I. So it will be 5I. And what is the intensity at B? Here phase difference phi is pi. Then it will be I1 plus I2 minus, because cos pi is minus 1. This is I into 4I0. 4I. Then you get I2 is, see I1 is I. Let me write first this I1 and I2. So this is 4I minus 2 into I into 4I. That means 4 will give you 2, right? So minus 4I here. So it will be only I. Then what is the difference in the intensities? Intensity difference will be del I so 5I minus 5I minus I. So this will give you 4I. So this is the answer. I hope now you are satisfied with this answer. So this is the general formula. You should remember this. Okay. Then you should know that this phi is phase difference. I1 and I2 are the intensities of the two beams coming up. Okay. And interfering. So this is how you have to solve this question. Let us see Third question. In YDAC, that means Young's double slit experiment, 12 fringes are observed to be formed in a certain segment of the screen. Okay, generally we see in the screen, okay, suppose this is 0, so you can see both up and down there will be fringes, okay, like this. I'm sorry. Fringe pattern will be like this with equal intensity in case of interference, okay, on both sides. All right, so dark and bright, dark and bright. So this is actually bright, so this will be dark, dark, this will be bright, this will be dark, this will be bright, like that it goes. And you know, the fringe width is actually, fringe width is denoted by beta. Fringe width denoted by beta. It is, suppose this successive, it is the difference between successive bright or dark fringes position. So if the positions are xn plus 1, suppose this is the position for this is xn bright fringe, and this bright fringe xn plus 1, then the difference between these two, that means this space is called fringe width. This space is called fringe width, and this fringe width will be excuse me, will be same for all other, like throughout the fringe pattern. Okay, so this is written as, like, if we know this will be d lambda by d, where d is the fringe width. Okay, d lambda by d, beta is equal to d lambda by d, or the separation between the fringe. No, sorry, this d is separation between the slits. Okay, in general it is written like this: beta is equal to d lambda by d. So beta actually the fringe width, that, so if I have beta known, then how many fringes has been formed in this region with within this segment. See, if I say in this segment, two fringes have been formed. Okay, two successive bright fringes. Okay, at least that I can say, isn't it? So in between two successive bright fringes have been formed. Anyway, so here I'll read the question for you. 12 fringes are observed to be formed at a certain segment. Total 12. Total 12. That means bright, dark, everything. Okay, total 12 in a segment of the screen when the light of the wavelength is 600 nanometer is used. If the wavelength of the light is changed to 400 nanometer, the number of fringes observed in the same segment of the screen is given by. So just wavelength has been changed. So what we have seen here, see, the beta fringe width is directly proportional to lambda. Okay, fringe width is directly proportional to lambda. That is what we have seen now. So then when the wavelength decrease from, so here wavelength has been decreased. See, earlier what was happening with 600 nanometer wavelength in YDAC, Young's double slit experiment, in a particular region 12 fringes were formed. Now wavelength has been decreased. In the same segment, how many fringes will be formed? This is the question. So we have seen that beta is directly proportional to lambda. So when the wavelength is decreased from 600 to 400 nanometer, the fringe width also will decrease because it is directly proportional. Fringe width will also decrease by a factor. What is the factor? The factor is 400 by 600. With this factor, that means 2 by 3 factor. Okay. Factor or the number of see, fringe width means okay, let me, or the number of fringes in the same segment will be increasing by a factor 3 by 2. Okay. Therefore, what earlier was 12, so it will be increased by a factor 3 by 2. So it will be 18 number. So when we have got from here the wavelength, so beta means fringe width, which is directly proportional to the wavelength used. So when the wavelength decreases, so fringe width also will decrease. See, in a same segment, if the fringe width decreases, then more fringes will be accommodated, right? That is very, very common sense. So if the fringe width decreased by this much factor, then the number of fringes will be increased by just reciprocal of this by 3 by 2 factor. This is not very complicated to understand, because see, in the same segment, if the fringe width decreases, then more by the factor the width decreases. With the same factor, the number of fringes will increase. I hope it is clear. I'll just repeat this again. See, in the same segment, okay, let me clean this portion a little bit. Suppose earlier there was a segment like this where there were 12 fringes total, okay, with 600 nanometer wavelength. Okay, now fringe width is directly proportional to lambda. Okay, now this case can be even treated in this way also. So you look here, so if the wavelength decreases, then the fringe width decreases. If the fringe width decreases, that means the separation between successive fringes, successive bright or dark fringes, is decreasing. That means they will actually accommodate more number of fringes within this region. So that is why when I'm saying that the fringe width decreases by a factor 2 by 3, 2 by 3 or by 2/3, then at the same time I can write that the number of fringes in the same segment will increase by factor 2 by 3, 3 by 2. Okay, because fringe width is decreased by that particular factor. So that's why the number of fringes will be 12 and that factor 3 by 2. So it will be 18. 18 fringes will be accommodated or created in that particular segment when the wavelength decreased to 400 from 600. All right, now this question is again interesting question. So here the question we are going to discuss now is also from Young's double slit experiment, but in this case it is little different than the previous questions. Here okay, let me first give you the options here. Options are A is equal to 2 lambda, B is equal to 2 lambda by 3, C is equal to lambda by 3, and D is equal to lambda. So in this question, an ideal double slit experiment, when the glass plate having refractive index 1.5 of thickness T is introduced in the path of one of the interfering beams. So you can think like this. Two interfering beams are there. Okay. One is, so suppose this place interference is happening and another goes from here. Okay. So in one of the path of the beam, a glass plate is introduced. Okay, in one path, this glass plate of thickness T having refractive index 1.5 mu, refractive index 1.5 is introduced in the path of one of the interfering beam of wavelength lambda. The intensity of at the position where the maxima, central maxima occurred previously remains unchanged. So here we know a formula. I'm not deriving this formula. You can find out this formula that when a transparent sheet, whether it is glass or something else, is introduced in one of the beam, like path of the beam, then the path difference will be introduced is mu minus of 1 into T. So this much path difference will be introduced. And if you see the shift of the central fringe, shift of the central fringe will be given by dx is equal to, there are two formula. I can write beta by lambda mu minus 1 into t, or beta I can write d lambda by d, so d by small d mu minus 1 into t. Okay, so this is the expression for the shift of the central shift in the position of the central fringe. So here in the question it is said the thickness of the glass is such that this shift is not occurring. This shift is not occurring. Okay, the position of the central maxima remains unchanged. Then what will be the minimum thickness of the glass plate? What will be the minimum thickness of the glass plate? I'll just repeat the question. In an ideal double slit experiment, when a glass plate of refractive index 1.5 of thickness T is introduced in the path of one of the interfering beam having wavelength lambda, the intensity at the position where the central maxima occurred previously remains unchanged. Sorry, this is intensity. I'm sorry, this intensity remains the same. Okay, at the same central position. That means the central position, position of the central maxima is occurring at the same place. That means the pattern shift in such a way that the nth bright fringe occurs at the position of the central maxima itself. Okay, then you have to find out the minimum thickness. So answer to this question is that the pattern is shifting. Pattern is shifting, and pattern shifts in such a way that the nth bright fringe occupies the position of the central maxima. Intensity is not changing. I'm sorry, not the position. The intensity doesn't change. Occupy the position of the central maxima. Okay. The pattern will shift in such a way that the central maxima and nth bright fringe, they will be at the same position. I'm sorry, in the other words, I should say the pattern shifts in such a way that the nth bright fringe occupies the central position. Okay, the position of the central maxima. See, in this case, I think I should draw the intensity pattern. If you remember also, you'll see the intensity pattern actually does not have decreasing or increasing intensity. Here, in case of interference, you know, whether it is central fringe or some other fringe, the intensity remains the same. Okay, in the pattern, intensity remains the same. So if suppose this pattern shift to this particular pattern shift to this, then the intensity remains the same. It is not changing. Intensity of the central pattern doesn't change. If in other words, if this, so if the shift is such that this minima goes to central pattern, position of the central pattern, if suppose the shift would have happened in a way that, yes, if this happens at the central region, the minimum intensity is occupying the central pattern, then you would have seen intensity variation over here after putting this thing. Okay, so you have to understand that intensity is remaining same. That is because some bright pattern is just coinciding at the central maxima, position of the central maxima now. So that's why for bright pattern we know we can then write d, suppose nth bright fringe, so d lambda by d into n equal to this capital D by small d mu minus 1 into t. From here, see, this says that nth bright pattern is coinciding with the central pattern now. Okay, so here it is said minimum thickness. For minimum thickness, we can put n is equal to 1. That means the okay, so n is equal to 1. Then what we get is mu minus 1 into t is equal to 1. Okay, sorry, not 1, this is lambda. Here you can just do one thing, sorry, you can just see here, oh, everything has gone. Anyway, I'll write it again. So options were 2 lambda, b lambda by 3, c, okay, b is 2 lambda by 3, this is c is lambda by 3, and d is lambda. So we have seen that nth bright pattern should coincide with the coincide or shift to the position of the central pattern, then only this can happen. So this is d lambda by d into mu minus 1 into t. So you look ultimately for minimum, as I was saying, for minimum thickness, we can write this n is equal to 1. Okay, when n is equal to 1, then we can write mu minus 1 into t minimum is equal to lambda alone. Okay, okay, this side there will be no lambda, I am sorry. Okay, so now t minimum will be lambda by mu minus 1. So mu is 1.5 minus 1, so this will give you 2 lambda. So the first option will be the correct answer for this question. Okay, now we'll go to the, I'll take up one more question. This I have to write the question, so let me give you the question here. The question is, Young's double slit experiment. I'm writing in short note. Young's double slit experiment is carried out by using green, red, and blue light. Blue light, one color at a time. Okay, one color at a time. The fringe width recorded are beta green, beta G, beta R, and beta blue small b, or let me write capital B itself. So capital B. So this is the fringe width when the light was used, green light was used, and that is the beta R is the fringe width when the red light was used, and beta B is the fringe width when the blue light was used. Now the question is, there are 4 options, you have to choose the correct option. Then beta G is greater than beta B, greater than beta R. First option. Second option is beta B greater than beta G greater than beta R. Option C says beta R is greater than beta B greater than beta G. And last option is beta R greater than beta G greater than beta B. Okay, so which among these 4 options are correct? Like option is correct? See, we know beta is directly proportional to lambda, right? And we know lambda R is greater than lambda green, and lambda green is greater than lambda B. Blue light has smallest wavelength among all these 3 colors. Okay, so red has the most, like longest wavelength, then green, then blue light has wavelength, least wavelength. So that's how we can say the option 4th, where the fringe width for red light is greatest, then this is greater than the fringe width for green light, and that is greater than that of the fringe width when the blue light is being used. So this is the answer for this question. So the 4th option will be the correct answer. Okay, so with this we'll stop here for today. Next day we'll pick up few more questions on interference pattern, interference. Okay, in the next day, and then we'll go for diffraction, and slowly we'll go to the polarization. Or maybe if this happens, that we can take up questions from all the topics together also. Okay, so bye for today. Thank you for your patience.